Hello guys, in today's video I want to talk about power factor. So before we'll get started, here I have a circuit set it up, but let's talk a bit about theory. So in electronics we have something what's so-called momentary power. And in AC circuits we got the AC voltage and the AC current that lags after, for example in an inductor, after voltage. And in some point we probe the voltage and the current and we calculate the value, and this is what is called momentary power. But of course what we care about is this phase shift before those two waveforms. So the second thing that we've got is an active power, which is RMS value and current multiplied, and then the power factor, which is cosine of the phase shift, and it's measured in watts. So right now, as you can see, if the phase shift, the power factor will be smaller than 1, it will be worse, getting more worse. But if the power factor will be 1, it will be the best situation. Then we have what's so-called apparent power. For example, transformers are rated with this value, and it is marked with S, and it is just voltage times current RMS values, and it's measured in volt-amps or volt-amperes, voltamperes, as you wish to call them. Reactive power, it's another thing that we will talk the most today, and it is marked with Q, voltage times current times sine of the phase shift, and it's measured in VARs. So as I said, the cosine of the phase shift should be equal to 1, and this is the best situation, and we'll try to make it this way. And then what we have is the phase shift needs to be 0 in order to have cosine of the phase shift equal 1. Then we have some other relationships between those different types of powers. So for example, the square of apparent power is equal to the active power squared plus reactive power squared. Then we have another formula, which is apparent power equals square root of active power squared plus reactive power squared. And here we have some relationships between reactive power and active power, and apparent power and active power. And here we have the tangent of the phase shift and the cosine of the phase shift. So here I've got an example circuit where we have just a simple resistor with a voltage across it and a current through it. And here we have some waveforms. Here we have the voltage, current, and power on this axis, and then on this axis we have time or angular speed, as we wish to call it, or velocity, angular velocity. Then here we have voltage and current without phase shift. So we have only active power here. As you can see, the active power, the voltage times current there, voltage times current there. So on both sides of the cycle, here we have positive value of the power, and here on this side of the cycle we've got positive amount of power. But when we will change our component to a real capacitor, not a real but ideal capacitor and ideal inductor, you will see that the phase shift causes our power to be returned to source, not drawn from it but returned. Same with a capacitor. There are different phase shifts, but both of them return some power into the transmission line, which is not good. So in our case, we'll be connecting a motor. So a motor will be a real coil. So it will be a coil that has here the impedance of it, so the whole thing will be equal to resistance, square root of resistance squared, and induct times squared, and this square root from that. Here we have the waveform, how it will look like. So we have a resistor, inductor, voltage across it, and current through it. And as you can see, the phase shifts and everything shows us that here we've got a small amount of the power returned to the source, to the transmission line. So let's right now do a practical implementation of the circuit. So we've got 230 volt AC, because that's the easiest and most common voltage that we have in our household, and we are using them in motors. So here we've got the 1 ohm shunt. Before it, we connect ground of our scope, which is insulated. Then we connect, after this resistor, first channel of the scope, and then after the whole thing we connect the second channel of the scope. So the blue waveform on my oscilloscope will be current, and the yellow waveform will be voltage. This is what we should see, a small little phase shift in current, and without the compensating capacitor, because as you were able to see, I showed you before that coil makes a phase shift to the right and the capacitor makes a phase shift to the left. So we can compensate for the inductance with a capacitance. So this will cause our power factor to be better. So less reactive power will be happening. And this is what we want to make. So without the capacitor, there will be some power returned to the transmission line or to the source, but with the capacitor, we shouldn't see it. So let's get to the practical implementation. I will connect the whole circuit. As you are able to see, that's what we've got. I will stop it on the scope, and I will zoom onto the scope a bit. So that's what we see on the scope. Yellow is the input voltage, which is 230 volts. Blue is the current that is nonlinear because of the nonlinear magnetization of the core of the motor. And then what we see here is the power. Of course, it's not a true sine wave because the current drawn by the saturated core probably is nonlinear. But what we see here is basically the power is positive, but some of it is returned here, and those small little spots returned to the source, and this is what we don't want to see. So right now what I will do is I will connect this capacitor before running the circuit like that, and you will see the difference. So right now I will connect the whole circuit with the compensation capacitor, register the waveform, and that's what you can see. Of course, there's a lot of noise in there because of this cap added, because a lot of line inductances is added, but anyway, current is a bit smaller right now, and it's shifted to the left a bit because of the capacitance. So right now we barely have the power that is returned to the source, and this is what we want to achieve. We want to make the power factor as good as it can be, and it's very commonly implemented in normal appliances, home appliances. So it's very important to know when you are designing a mains powered circuit and it's an inductive, for example, load that you are driving, for example, like a motor, you should think about compensating it with a small cap like this one. The cap obviously should be rated like X2 or Y1 capacitor, and it should be rated for mains frequency. See you guys next time, and have a good day.